Okay, beam width, I will simply tell, if you have beam like this, if this is your maximum electric field, okay, here you are getting maximum electric field in this direction, then you fix the point where your electric field is at least max Emax divided by root 2, Emax divided by root 2. That means what? 70% of the maximum electric field. Similarly, you fix here. If it is a power, simply 1 by 2, P by 2. If it is electric field, simply by root 2. Okay, every voltage current you take by root 2, similar manner. Okay, then you connect the lines. Okay, you connect the lines like this. Okay, connect the line like this. Then you measure the angle. You measure the angle between this. Okay, this will give you the beam width. This will give you the beam width. This beam width is called as half power beam width. Half power beam width, because voltage is by root 2, then power is definitely by 2. So okay, this beam width is called half power beam width. If somebody measures the beam width like this, say I try a tangent line here, tangent line here, and tangent line here. If somebody measures the beam width like this, then that beam width is called as beam width between the first null. That beam width is called as beam width between the first null. In general, the beam width between the first null is 2 times of the half power beam width. So in general, beam width between the first null is equal to 2 times of the half power beam width. In general, I am telling, not necessarily to be always true. Okay, sometime it may fail, but in general, beam width between the first null is 2 times the half power beam width. That's okay. So now, so very clearly, once if you go from isotropic to practical 1, 2, 3, the beam width is decreasing. The beam width is decreasing. But what is increasing? The directivity is increasing. See, directivity of the one antenna, 2 antenna you measure, 3 antenna you measure, then definitely for third antenna only directivity is very, very more, because this is value more. Once if you divide by the isotropic value, so directivity of antenna 3 is much, much more. So what is happening? The directivity of antenna 3 is much larger. D3 is larger as compared to D2, D1, and then D isotropic. And what is happening to the beam width? Okay, what is the beam width of isotropic antenna? Anybody?
4 pi.
4 pi. Half power beam width. Can you measure half power beam width here? Because here power itself is not changing. Everywhere it is same. What is the beam width between the first null? Okay, think over it. But definitely the beam width of isotropic antenna is greater than the beam width of this one. Okay, so when I use BW means that is beam width, sir. Please note down, BW means what? Beam width, not bandwidth, beam width. Mostly in antenna notation, BW means beam width. Very rarely we will use bandwidth, but in general, BW means beam width. So beam width of the third antenna is much, much smaller as compared to the beam width of the second antenna, as compared to the beam width of the first antenna, as compared to the beam width of the isotropic antenna. Isotropic antenna is having large beam width. So from these two relation, if you have more directivity, then it will have less beam width. If it has less directivity, then it will have more beam width. So that means what? The directivity and beam width is always inversely proportional to each other. The directivity and beam width is very, very important. The directivity is always inversely proportional to beam width. Very, very important relationship. What it is telling, if your signal, electromagnetic signal, has to go for longer distance, then the area of the coverage of your antenna has to be less. Okay, what it is telling, if your directivity has to be high, that means what? Or another way you can think it of like that, your signal has to go longer distance, because once if you have directivity, you will have more power. If you have more power, you can, your EM wave can go longer distance. Okay, longer distance, because for receiver to operate, you need some minimum power. Okay, then until that your EM signal can go. So if you want to go longer distance, then definitely your beam angle of the antenna, beam width of the antenna has to be less. If your antenna is radiating in all direction, then it will have more beam width, but it will have less directivity. Okay, less directivity, it will have less gain, or otherwise it cannot go longer distance. Okay, what is D? If D is high, what is the advantage? If D is high, power, anyway gain is high, power received is high. Once if power received is high, because if you can if you are able to operate satisfactorily with some minimum power, or say you need 1 watt power to operate properly, but if you are getting 10 watt means what, sir? That signal can go still longer distance, until some people may receive 1 watt. If it goes longer distance, then the range of operation can be increased. Okay, power received increases. That means what? Indirectly you can increase the range. Indirectly you can increase the range. Okay, so once if you have more directivity, then you can receive more received power. Power received will be more, or otherwise range can be more. Range can be more. Okay, so that is the idea. That is the idea. Then what is beam width? If beam width is high, coverage area is high. If beam width is high, coverage area is high. That's it. If beam width is less, coverage area is less. If beam width is less, coverage area is less. Coverage area is less. That's another way. But beam width and directivity is always inversely proportional to each other. Inversely proportional to each other. Okay. Now we'll try to derive some other definition for directive gain and directivity. Okay. Okay, so we'll derive, but simply just a derivation, but no need to remember. I will tell you what to remember, what not to remember later. Just listen the derivation. Okay, so again, you know that the average radiation intensity U bar can be written as R square P radiated, or radiation density or power density. Okay, so again, this is true only in case of isotropic. That's why I'll write iso here. Okay, this is true for isotropic case. Okay, so from this, what is clear, then how can you modify this equation? The power radiated that isotropic, power radiated isotropic is equal to u bar divided by r square ar cap, r square ar cap. Now suppose I want to measure what is the total power radiated by the isotropic antenna. Okay, what is the total power radiated by the isotropic antenna? Actually, some hint is there. I will tell you later, but I will go by regular procedure. The total power radiated by any antenna or isotropic antenna. If it is isotropic antenna, this is 0 to pi because it radiates uniformly in all direction. Okay, that means you can use maximum value of theta and maximum value of pi. Okay, this goes from 0 to 2 pi. And what is the power radiation density? PRD and DS, PRD and DS. Okay, actually, I'll first. Okay, actually, this is the integral. Then what I can do, say one is theta and another one is pi. Okay, so for isotropic, my theta can go from 0 to pi. My pi can go from 0 to 2 pi. What is the power radiated in case of isotropic? That is U bar divided by R square. That too, the direction of radiation is always radial direction, AR cap. Then you know what is the ds vector. Okay, ds, generally this is a vector, this is also a vector. Okay, ds means what, sir? Ds means, okay, so r square, okay, dot, this is 1, again dot product with r square sine theta d pi ar cap. Again, you know ar cap cancels because dot product is 1, then you concentrate about remaining things. And I can write this, because this u bar for isotropic radiator, this is constant because u is generally function of angle, but for isotropic radiator it is independent of angle because isotropic radiator radiates uniformly in all direction. Okay, once if I have radiation intensity of isotropic radiator in future, I can put it as u naught because the radiation intensity of isotropic radiator is uniform in all direction because it is independent of direction. But for practical antenna, that depends on direction. So that's why I will modify this one as U naught, because I have taken this relationship for isotropic radiator. So once if we take U outside, that I can put it as a U bar, sorry, U naught, and again 0 to pi, 0 to 2 pi. Okay, r square cancel, then sine theta d pi. Once if you do all this integral, then that is U naught into 4 pi, U naught into 4 pi. Okay, so omega radiated isotropic is equal to U naught into 4 pi. Okay, then what is U naught? U naught is equal to omega radiated isotropic divided by 4 pi. Okay, this only in the beginning itself I told you, whenever you have U naught, what is U? U means total power radiator divided by solid angle. Total power radiator divided by solid angle. Okay, you can take like this. You know what is total power radiated in case of isotropic radiator, W radiated iso. And you know what is the solid angle of isotropic radiator, that is 4 pi. And this is constant because this is independent of direction. Okay, finally you will have some value, but that is independent of theta. So you can write U naught is equal to omega radiated iso divided by 4 pi. So what I am telling, in future, please don't do all this derivation, simply you remember this. Okay, what is this definition? U naught, the two for isotropic antenna, total power radiated divided by solid angle. I know the solid angle of isotropic radiator, that is 4 pi. I know what is the total power radiated in case of isotropic. Then if you make a ratio, then you will get average radiation intensity of isotropic radiator. Okay, isotropic radiator. Now, why I have derived this formula, I am going to make. See, I know the directive gain. Directive gain means one formula we have used like this. What is the